Welcome to Habitable Planet Lecture 3. Today we're going to be talking about the Big Bang, how everything began. In this lecture we'll answer questions that are fundamental to all of us and how we got here. How big is the universe? How old is the universe? Was there a beginning? How do we know? The main points of this lecture are first that our natural inclination of human curiosity, what Aristotle said is that human beings by nature have a desire to know, by nature are curious. How that curiosity gradually leads to understanding, knowledge, answering simple questions like how far away the moon is, and out of this curiosity, suddenly appearing like an amazing discovery that could never be predicted, was the evidence for the Big Bang. To determine the distances to celestial objects, beginning with the moon, required bootstrapping methods, and these methods took thousands of years of human history where we could determine the distance to the moon, then the distance to the planets, then the distance to the sun, then the distance to the stars, then the distance to galaxies. Investigating the chemical compositions of galaxies by looking at the spectra of the light they emitted showed the surprising result that they're all moving away from us. And then if you plot how far away they are, their distance, versus how quickly they're moving away from us on two different axes of a diagram, all of the data plot on a straight line. And we'll see that that straight line indicates that everything in the universe began at the same place and at the same time 13.7 billion years ago. Then there was a serendipitous discovery of the background radiation of the universe, which was a stunning confirmation and proof of the Big Bang, which makes it an entirely accepted theory. Now we're going to be talking about distances that are extreme. So each one of these ticks on this slide is a factor of 1,000. So here is the Earth diameter in centimeters. There's the diameter of the Sun, about 100 times bigger than the Earth. Then there's the diameter of the Earth orbit around the Sun. And the solar system is in here somewhere. The distance to the nearest star, the diameter of our galaxy, the distance to our nearest neighbor galaxy, the distance to the galaxy with a retreat velocity 1/10 the speed of light, and so on. So you see we're talking about 10 to the 18th difference in distance, huge numbers. And because those numbers are huge, we don't use centimeters, we use numbers like light years. So 10 to the 27th centimeters is 10 to the 9th light years. Human beings from the dawn of time have looked up at the sky with wonder and wondered what was there. And if we look at this image, one of the most obvious features of it is that it's mostly black. There are stars and planets. In this portion of the night sky, you're seeing the constellation Orion with his belt here. Some stars are brighter than others. But the fact that most of the star is black led thinking people to wonder about a particular paradox, which was called Olbers' paradox. Olbers in 1826 said that if the universe is infinite and steady state, then the sky should be light everywhere, because you may go along a trajectory and not hit a star as you look in this direction, but because you can look infinitely back in space and time, eventually you'll hit a star, and that's true everywhere, and so the sky should just be covered by a constant canopy of starlight. How amazing would that be? But it's not. It's mostly black. So maybe the universe is not infinite. Maybe there's just a finite number of stars that we're looking at. But that leads to another problem, because if the universe is finite, it should collapse. It means it would have an edge somewhere, and having an edge somewhere like this, there would be gravitational forces, and the universe should collapse. Galaxies on the edge feel an inward tug of gravity. So the universe cannot be infinite. If it were, stars would be everywhere. And the universe can't be finite, because if it were, it would just collapse. Lemaitre, in the early 20th century, proposed a solution, that the universe is finite, but it's not static. It's expanding like an exploding egg. This was an interesting conjecture, but there was no evidence for it at the time. Starting thousands of years before, people had been asking questions about how far away things are that are up in the heavens. For these questions, astronomers had to devise ways to measure distances to distant objects. And the simplest way, devised by the Greeks, was to use geometry. We'll get to these other methods later on. So geometry, you remember from when you took it in junior high school or high school, that you can determine a triangle if you know angle, side, angle. So if you have a rock out in the middle of a lake somewhere, or an island, and you have a baseline along the shore that you can walk along, you can measure the angle from this point on the baseline to the rock, and the angle from this point on the baseline to the rock. You know the distance along the baseline, so you have angle, side, angle, and that determines the shape of the triangle, and you can calculate the distance to the rock. A slightly more complicated method, but by the same principle, is called parallax. If you have a baseline, in this case we're showing the orbit of the Earth around the Sun, and you want to know the distance to a close star, you can measure it in spring and in the fall, 6 months apart, and you can see how the angle of the star changes against the background that's distant from that star. And by measuring that angle from two different points in the Earth's orbit, you have angle, side, angle, and you're able to determine the distance to the star. But the angles are only measurable for nearby stars in our galaxy. The Hubble Space Telescope can use this method for stars a few thousand light years away. This method requires knowing the length of this baseline. And the length of this baseline requires knowing how far away the Sun is. How do we know how far away the Sun is? Well, the first question that the Greek answered was, how far away is the Moon? They were in communication with one another. So it turns out that when there was a total eclipse of the Sun in Turkey, communication showed that in Egypt there was not a total eclipse of the Sun. It was partial. So here's the Earth, here's the Moon, here's the Sun. So when there's a total eclipse and you're standing somewhere on Earth, your line of sight goes off this way. It's blocked by the Moon. You can't see the Sun on this side. And it's blocked by the Moon. You can't see the Sun on this side. The Sun is fully eclipsed. But if you move around on the Earth's surface, now your line of sight is these blue lines. You can see that this line just grazes the edge of the Moon, and this line would be going through the Moon, so the Moon is blocking out half the Sun. But when you look off in this direction, you see the Sun. It's a partial eclipse. Well, this is just the geometry we were talking about, where you have a baseline, which would be the distance between Turkey and Alexandria in Egypt. You have the Moon, which is some distance from your baseline, and you have a background, which is the Sun. And so by looking at the difference of the angles, you're able to determine the distance to the Moon. They did a remarkable job. They got the distance right to about 5%. 1600 years later, Kepler was able to discover his laws, and those laws revealed the relative distances of the planets from the Sun. You knew that if the Earth was 1, Venus was 0.62, and Mars was about 1.6. If you knew any one of those distances, you could determine them all. But how could we determine the distances to any one of the planets? It turns out a way to do this is to use what's called a transit of one of the planets across the Sun, in the case of Venus. Venus transits across the Sun once every 100 years, and it does it twice, 7 years apart. So here's Venus, here's the Sun, and if you're at point A on the Earth, Venus, when it crosses the Sun, is crossing it down here. And if you're at point B on the Earth, Venus, when it crosses the Sun, is crossing it up here. So the transit of Venus seen by observer B is up here, and the transit seen by observer A is down here. Of course, this is all greatly exaggerated for clarity. So all that was necessary was to determine the transit of Venus from different places around the Earth. Halley, famous for the discovery of Halley's Comet, realized this would be a wonderful way to determine the distance to Venus, and from the distance to Venus to also know the distance to the Sun. So they tried it. And the first experiment, it was cloudy, they didn't have people set up properly, and then they knew that 7 years later they would be able to try again. So they set out expeditions around the world. Cook's expedition, famous Cook Exploration Division, was one of these. And he landed in Tahiti at the time when Venus was going to be transiting the sun. And this could be compared to other measurements that would be made in South America and in Europe and in North America. And by making these measurements at different places around the Earth, it would be possible to determine how far away Venus was from the Earth, and from that to determine how far away the sun was. This was international collaboration, great planning, hundreds of years ago. Once you know the distance of the sun, then you have the long baseline that we mentioned earlier, which gives you the ability to determine the distances to the nearest stars, a few thousand stars. All right, there are lots of stars you can't determine the distance to. So how is it that we can determine distances to stars that are farther away? Well, it turns out that stars have different brightnesses. And through the spectra of stars, it's possible to know how bright the star actually is. That is, to determine, if you like, the wattage of the star. And if you know the wattage of the star, by seeing how bright it appears to us on Earth, you can determine how far away it is.
Brightness of a star depends on the color of the star. So by looking at a star and looking at it through a prism, you can see its color. And from its color, and you know how far away it is, you can determine, oh, stars of different types have different wattages. They have different brightnesses. So by looking at the spectra of the star, we can tell how hot the star is. That's cool. So now, if we look at a distant star that I don't know how far away it is, I still know how bright it is. Is it a 100-watt star? Is it a 1-watt star? Is it a 1,000-watt star? I know its brightness. And then I can see the brightness that I actually perceive in the telescope. And in that way, you can tell how far away that star is. So let's see what that means. So here's a star. And I have a light measure here, which is going to appear on the screen over on this side. And you can see it's a value of 4. You see it? So this light source is 1 meter away from the measuring device. And now I'm going to move it 2 meters away. And as I move it 2 meters away, as marked here on the ground, the intensity of light that's received is 1 instead of 4. So if you know the brightness of that bulb, and you measure its intensity on the meter, which you can use with a telescope, you know how far away the star is. And if I moved it 4 meters away, then this would go down to 0.25. And if I moved it even closer, it would go up to 16. Or if it were a duller star, so there, that's a 4 star. If we made it just a 2 star, well, we know that the star is less bright. And we move that another meter away. You need sensitive instruments. I can't even read it up there, but if I go down here, it's down to 0.5. It's dropped by a factor of 4. So in this way, by taking a star and knowing what its wattage is, knowing how bright it is, you can, by measuring how bright the light is that you receive at your telescope, you can tell how far away it is.
We can see this visually if we just take a picture of a street like this, and all these street lamps have the same wattage bulbs on them. But you can see as you get further and further away, the bulbs are less and less bright. So if we know the wattage, we can use that to determine the distance. One additional way of determining the wattage of a star is to use stars that actually vary in their brightnesses. And Henrietta Leavitt, one of the first early famous female astronomers, discovered that the pulsation period, that is the distance between bright, dim, bright, the distance between the two bright points, correlates with how bright the star is. So by using stars that she knew how far away they were, she could make a diagram calculating the period of the luminosity variation versus the luminosity of the star. And there was this very nice correlation. So if you look at a star in a distant galaxy where you may not be able to get enough information from the spectrum to tell you what the wattage of the star is, if it's varying in its luminosity, this is in a in another galaxy called M100. And if you look at the center of these images, here you see it's bright, and there you see it's decreasing, and here you see it's faint. So you can see how the star is pulsing, and by measuring the period of the pulse, you know how bright it is. And by knowing how bright it is, you can then measure what its actual brightness is, and in this way, you can determine the distance to this galaxy. Very cool. For more distant galaxies, you need even brighter light sources. And a brighter light source is a Type 1a supernova. That's an exploding star which in a short period of time emits huge amounts of radiation, equivalent almost to the entire light coming out of a galaxy. And these Type 1a supernovas all have about the same brightness. So by looking at supernovas, it's possible to tell how far away more distant galaxies are. And these things are so bright you can detect them even from distances as far as 10 billion light years. Now, another way of determining how far something away is to use a standard ruler. So if you know an object's actual size, you can just see how much of an angle it takes on the horizon and calculate its distance from simple geometry. So if you take your cell phone and you hold it close up to your eyes and you look at the background, you can see that it occupies a lot of the wall that you're looking at. Or you could set it up so that it occupies your entire computer screen. But if you then move it away from yourself, the farther away it is, it doesn't occupy the entire computer screen anymore. It just occupies a little portion of it. And the further away it gets, the smaller and smaller amounts of the computer screen that it occupies. So by knowing the size of your cell phone, you can tell how far away it is depending on how much of the horizon it blocks out. This is a way to determine the distances to galaxies that are very far away. Galaxies have a particular collection of sizes, and by looking at the nature of the galaxy, you can make estimates of its size. And then you can see how much space it takes up in the photograph of the universe, and by seeing how big the galaxy appears, you can tell something about its distance. So that's a bootstrapping method. First, determine the distance to the moon. Then determine the distance to Venus. That gives you the distance to the sun. That gives you a bigger baseline. Then you can determine the distance to near stars. When you determine the distances to near stars, then you can start using the brightness of stars, and that takes you farther. And then you can even use even brighter objects to determine the distances to nearby galaxies. And then Type 1 supernovae to tell the distances to distant galaxies. And galaxies that are too distant for any of these methods, you can use how big they appear in the sky to say something about how far away they are. An amazing 2,000-year journey to discover the distances of objects in the sky. Another natural question is, well, what are stars made of? Are all stars made up of the same stuff? What are galaxies made of? And to answer this question was also a long series of discoveries where the original question of what is a star made of, which would have seemed so inaccessible when it was first asked, gradually became able to be addressed very clearly. Newton, in addition to the laws of gravitation, made very important discoveries about light and showed that white light, or sunlight, if you put it through a glass prism, broke up into a series of colors. And these colors are caused by having different wavelengths, and those different wavelengths are bent differently as they move through the glass prism. It turns out there's a huge range of wavelengths, and the visible wavelengths that we see are only a small part of this electromagnetic spectrum. We talk about the higher frequency of waves, that is, when there are more waves for a particular distance, and they have a shorter wavelength. And the lower frequency of waves, less frequency for time, and they have a longer wavelength. So high frequency, large numbers going for a given unit time, shorter wavelengths. Low frequencies, less complete waveforms in a given period of time, and longer wavelengths. Here's the electromagnetic spectrum going from gamma rays all the way out to radio waves. And our eyes are designed to see light only in a very small portion of this spectrum, in the visible spectrum. As discovery of the properties of light were moving forward, chemists were discovering the elements and their properties in more or less the same time frame. It was in the middle of the 19th century that the periodic table of the elements was discovered. And as the early chemists played with different elements, they found that each element, if you heat it up or excite it, emits its own characteristic wavelengths of light. It turns out that's because each element has electrons that can move from one energy state to another, and they move in quanta. They jump energy levels. It's not continuous. And as they jump in energy levels, they emit certain radiations, and those certain radiations are wavelengths of light. So if you, as you'll see in a moment, when you have different elements and you excite them, they have different colors. Lithium has this beautiful red color. Sodium has a bright yellow color. This is sodium here. And copper has this nice green color. So when you see these different colors, it's telling you something about the chemical makeup. You can try this yourself. If you have a gas stove, take a little bit of salt and throw salt into the flame, and you'll see a bright wavelength of yellow being emitted as you throw the salt in the flame. So these wavelengths that are emitted are very specific. So when you look at sodium, for example, it emits 2 wavelengths in the yellow region. That's why you see a yellow light. And when you have lithium, its strongest wavelength is in the red region. That's why you see a bright red light. So if you want to know the chemical composition of something, you can simply take it, excite it in a torch, and by looking at the intensities of the lines that are emitted, you can tell how much of particular elements there are. So the wavelengths are a kind of fingerprint, and their intensity is also a measurement of composition, of how much of something there is.
This is our tower of spectra. It has an incandescent light up top, and then 3 spaces for gas discharge lamps. We have hydrogen, helium, and neon. If we turn these on and put on diffraction grating glasses, we can see the black body spectrum of the incandescent light and the line spectra of each of the gas discharge lamps. So since we can't give you diffraction grating glasses, what we're going to do is put the diffraction grating in front of the camera lens so that the camera can then look off to the side to see the spectra. Tungsten filament. Hydrogen. Helium. Neon. And now, the tower of spectra.
So by looking at the wavelengths emitted, you can tell what elements are present. And from the intensity of the wavelengths, you can say something about how much of the element is there. How cool. So, wait, we could look at the light from the sun and tell what elements are present in the sun and what their proportions are in the sun. How cool would that be? And so this was done, and the way this works is that a hot, dense object like a star emits a continuous spectrum of radiation of different wavelengths. And then there's an atmosphere around the star, and that absorbs wavelengths that are characteristic of the elements that are in that cloud of stuff around the star. And this leads to dark lines in the spectrum. So if you look at the spectrum of a star, it's a continuous rainbow, and it has dark lines in it. And these were first discovered by a German scientist by the name of Fraunhofer, so it's called the Fraunhofer spectrum. The Fraunhofer spectrum looks like this. This is the spectrum of the sun. It has sodium in it. You can see the two lines in the yellow region. It has hydrogen in it. So here's a very strong hydrogen line, and here's another strong hydrogen line, and you see that they're there in the sun. And by looking at all these different hundreds, thousands of lines that are in the sun spectrum, you can tell all the elements that are there and how much of them there are. So, what's next? Of course, if you're an astronomer and you've seen the sun spectrum, you would ask, gee, I wonder what the spectrum looks like if we look at other stars. Or what if we look at distant galaxies? Are all stars the same composition of the sun? And when this was done, it was discovered that the light from other galaxies was weird. So here's the image for light from the sun down here. And if you looked at a nearby galaxy, which appears to be pretty big, you saw a whole series of lines, but they weren't in the right place. And if you looked at a more distant galaxy, again, there was a whole series of lines, but they weren't at the corresponding wavelengths corresponding to the elements. What was going on? Well, the Fraunhofer spectrum is like a barcode. It has different intensities and different spacings. And if you look at these different spectra, you can see that the barcode is the same. It's just shifted towards the red. So this one is shifted a little bit towards the red. This big band corresponds with this one. These two lines correspond with those two. This corresponds with this one. And the further and further away the galaxy is, the more the lines are shifted to the red. This is the famous red shift. So what is a red shift and how does it happen? So here we're going to have an example of the Doppler effect using sound. So this ball that Alan is holding is going to be emitting a constant tone, which you can hear. But as he swings it around his head, if you just listen, you can hear the sound getting higher as the ball moves towards you, and cold and lower as it moves away from you. The ball's always emitting exactly the same tone, but what we hear varies depending on whether it's moving towards us or away from us. It applies to light. It applies to anything with a frequency. So you can take, for example, say that there were people doing football tryouts, and there's a quarterback sitting at the base of in the end zone, and the coach says, okay, receiver, run away from the quarterback at 10 yards per second, and the quarterback will throw the ball at 20 yards per second. So he'll throw one ball per second, and let's see if you can catch him. So the receiver takes off, and he runs 10 yards, and the quarterback throws the first ball. The receiver goes another 10 yards. Now that's 20 yards, and the ball has traveled 20 yards because it goes 20 yards per second. And the receiver catches the first ball. As he catches the first ball, the quarterback sends off the second ball. The receiver runs 10 yards. It takes him a second. The second ball has only gone 20 yards, so it hasn't reached him yet. Then he runs another 10 yards, and now the ball goes another 20 yards, and he catches it. So he caught, in 4 seconds, 2 balls. But the quarterback was supposed to be sending 1 ball per second. So he goes back and screams at the quarterback and says, "You're supposed to be sending 1 ball per second." All right, the coach says. Don't worry about it. We'll start it the other way around. You start from the other end zone, and you'll be running towards the quarterback this time. And after you catch the first ball, then you catch all the rest of the balls which the quarterback is throwing at 1 ball per second. So the quarterback's throwing 1 ball per second. It takes 5 seconds for the first ball to reach the other end zone. Quarterback has a very good arm. And by the time the receiver starts running from the other end zone, there are already 5 balls in the air. So when he's taken 10 seconds to run the 100 yards, he's caught 15 balls instead of 10. Now he's really furious because he says the quarterback did not throw 1 ball per second because he caught 15 balls in 10 seconds. This is red shift and blue shift. When the receiver is moving away from the quarterback, the frequency was lower. The quarterback was throwing 1 ball per second. The receiver got 1 ball per 2 seconds. When the receiver was running towards the quarterback was throwing 1 ball per second, but the receiver was catching more than 1 ball per second. It applies on all times. So the Doppler effect is that the frequency that is received can be different from the frequency that is sent if 2 objects are moving away from one another. So the football player was receiving 1 ball per 2 seconds. That's the frequency he received. But the frequency that was sent was 1 ball per second. And that big shift from 1 per second to 2 per second happened because the velocity of the runner, of the receiver, was 10 yards per second, and the velocity of the ball was 20 yards per second. And so there's a factor of 2 there. If the runner had been running faster or slower, the frequency would have been different that he had received. It all depends on the relative speed of the sender and the receiver. So when we look at the light from distant galaxies, what we are looking at is red-shifted light. And we know that it's red-shifted because we know the frequency that was being sent for the lines of the spectrum. So for this element, for example, you have these series of lines that make a big dark band here. And we see in a nearby star that the position, the frequency of that band, is exactly the same as we measure in the laboratory. But if we look at the light from a distant galaxy, it's emitting the same frequency because it has the same elements, but that frequency has been shifted. And all of the lines are shifted exactly the same amount. So the lines of the spectrum tell us the frequency that's being sent. The position of the lines in the spectrum in our telescopes tell us the frequency that is being received. And the amount of the shift of the lines tells us the velocity of the galaxy. But wait a minute, all these spectra go from blue to red. What's happened? Well, this galaxy up here, these lines have been shifted all the way from this point over here in the dark blue all the way over to the green. And what that means is that the light that we are seeing from this galaxy that is received as purple today was originally in the ultraviolet, and it's been shifted over to the purple. And that's what our eyes can see. We can only see red through purple. That's our sensitivity. And so we couldn't know just by looking at the spectrum of the star if it's any different. We need a telltale sign of what the frequency was that was being sent. And the telltale sign are the elements. So all galaxies are redshifted, and that means they're all moving away from us. So the universe is expanding. Olbers' paradox is resolved, and Lemaitre was right. The universe is an expanding egg. The next step was when light from many galaxies could be measured and compared to the distance of the galaxy, which had been determined by the bootstrapping method that we discussed earlier in the lecture. Hubble discovered this in 1929, and while the data over here are a bit hard to see and are obscure, he found that when you had a nearby galaxy that appears relatively big in the sky, it had a small red shift. And when you had a distant galaxy that was really far away, it had a huge red shift. And when you plotted up the data, it turned out that the retreat velocity of the galaxy determined from the redshift, correlated with the distance of the galaxy, determined by various methods. It's essentially linear. So what does that mean? It means that all the galaxies were together at the same time and the same place, and the time when they were together is determined by the slope of these data. Because the retreat velocity of the galaxy is distance over time, and distance of the galaxy is just distance. So when you divide distance by distance over time, you get time. And so the slope of this line gives you the time, and that's the time of the beginning of the universe, and it comes out to be 13.7 billion years ago. Okay, so at time 0, or very near time 0, the recession velocity of the galaxies was different. Some were going faster and some were going slower. After 5 billion years, the fast one would have gone to here and the slow one would have gone to here. After 10 billion years, the fast one would have gone to here and the slow one would have gone to here. And so with time, this line progressively gets less and less steep on this diagram, and the slope of the line is telling us the age. All right, since all galaxies are moving away from us, does this mean we are the center of the universe? Well, it turns out the universe is constructed in such a way that everyone can feel they're in the center. So a convenient, not completely accurate, but nice analogy for this is to imagine a piece of raisin bread. In the raisin bread, you have expanding when it has the yeast, and so the raisins were all close together, and as the raisin bread expands, the raisins all move apart from one another. Every raisin sees every other raisin moving away from it. So the space between stars and galaxies is increasing everywhere, and no matter where you are in the universe, you can get to think that you're in the center. Of course, the universe is expanding much more than raisin bread. So it started out as a little dot, and now it's immensely vast. So you can think of it more as something like is shown on this slide, where you start out with some small universe with the galaxies relatively close together. And then with time, the universe expands magnificently, so the galaxies keep getting farther and farther apart. All right, so I've got another little simple analogy to exemplify this. I don't know whether you have this experience. You may have it if you have kids, that when you have a small kid, you want the birthday to end at a particular time. So you say, the birthday party runs from 2 to 3:59. The subtle hint being you're supposed to leave at 4. So everybody leaves, and everybody leaves at the same time. But the host family is conscientious, and so they ask everyone to send back to them their position and their velocity 1 hour and 2 hours after leaving the party. So one person's walking. At 3 miles an hour, after 1 hour, they're 3 miles away. After 2 hours, they're 6 miles away. Another person's on a bike, 10 miles an hour, so 10 and 20. In a car, 30 miles an hour, 30 and 60. And there's a rich person with a helicopter, 200 miles per hour, so 1 hour, 200 miles, 2 hours, 400 miles. So the birthday party giver decides to make a plot of the data, and so they plot up the distance that they are away versus the speed that they're going. And so there it is. They're going 200 miles an hour, and they're 200 miles away. And they were going 30 miles an hour, and they're 30 miles away, and it all plots on a straight line, and the slope of that line is 1 hour. And after 2 hours, 200 mile an hour person has gone 400 miles, so the slope of the line is 2 hours. So the slope of the line gives the time when everybody left the party, if they left the party at the same time. And that's the situation with the universe. So, to sort of sum up where we are at this point, through thousands of years of investigation, human beings were gradually able to discover how far away things were in the sky. And the distance of galaxies could ultimately be determined using standard candles and galaxy size. How fast are the galaxies moving? The velocity can be determined from the redshift, and that shows that all galaxies are moving away from us. Then it turns out that remarkably the velocity and distance correlate, showing that all the galaxies were together at the same time in the same place 13.7 billion years ago. So it's a good hypothesis. It's cool. It's a 2,000-year history of human curiosity and just trying to answer basic questions like how far away are things and what are elements made of and what happens if you heat up an element to high temperatures. But all good hypotheses need to be confirmed, and the Big Bang was controversial when it was first proposed, and its stunning confirmation happens about 40 years later. So the further evidence for the Big Bang, the big one, the big evidence, was the cosmic microwave background, that is the overall temperature of the universe. And then once nucleosynthesis was understood, it turns out you could calculate how much hydrogen and helium should be made during the Big Bang, and the ratio of hydrogen to helium turned out to be just right for a Big Bang event. So these are the two major new lines of evidence. We'll only talk briefly about this one because we haven't talked about nucleosynthesis yet. But this is actually quite an interesting story. As we mentioned earlier, the electromagnetic spectrum extends from very short wavelengths like X-rays to very long wavelengths like radio waves. And our eyes are sensitive to this very narrow portion of the electromagnetic spectrum, but you can get goggles that are sensitive to the infrared and can see heat, and we have radio antennas, and the radio waves are all around us, passing through us right now, but when we have a radio antenna, it is able to pick up that signal, and TVs can pick up the TV signals that are all around us. And when we go into a doctor and have an X-ray taken, those are the waves through the X-rays. We can't see them, but they're so energetic that they pass right through our body and reveal the different densities within our body. So it turns out that every object that has a temperature emits radiation associated with that temperature. So if you look, for example, at the spectrum coming from the sun, it looks like this, and that gives us an indication of the temperature that the sun is emitting, not the temperature of the interior of the sun. And if we compare that to a black body curve, it's a very good fit. Of course, it has all these little dips in it. Those are the Fraunhofer lines, where it's actually not emitting radiation. So in this demonstration, you're going to actually visualize black body radiation. Black body radiation is being emitted from every object. It's just that most of the radiation that's emitted is not in the visible range, and therefore we can't see it with our eyes. If we want to see black body radiation, we have to heat things up to higher temperatures, in which case the radiation becomes visible. So in this demonstration, you're going to actually visualize black body radiation. Black body radiation is being emitted from every object. It's just that most of the radiation that's emitted is not in the visible range, and therefore we can't see it with our eyes. If we want to see black body radiation, we have to heat things up to higher temperatures, in which case the radiation becomes visible. So here we begin with an oven, which we're going to heat up to 1,000 degrees. So there's the oven, there's the temperature showing it's up at 1,000 degrees. And if you open the oven, you will see that it has a bright color, a bright orange color. In contrast, the iron ball and the brick just have their normal reflected light colors having nothing to do with black body radiation. So we're going to heat them up inside the oven and see what happens. And after they've had enough time to heat up, they acquire the same color as the oven itself, because all the objects have the same temperature and therefore emitting the same black body radiation. Room temperature, 1,000 degrees. When they acquire that temperature, you can see it. If we take them out of the oven and put them on this asbestos plate, then gradually they're going to cool down, and the intensity of the radiation and the overall colors are going to change. This was bright orange. You can see it's getting dimmer and dimmer. Now the outside of this is cooled so much you can't see the black body radiation anymore. You can just see it on the inside. And as this cools more and more, it becomes less and less bright. Dimmer and dimmer, less and less orange. The black body radiation is still being emitted, but we can just barely see it there at the end. So every object emits black body radiation. Sometimes it's perfect, sometimes it's a little less perfect because of chemical effects and so on. But you can tell the temperature of an object. When the black body radiation gets hot enough, then the wavelengths move into the visible spectrum and we can see it. That's why things get red hot, like you just saw in the demonstration. But things that are much colder, like us, for example, we don't emit black body radiation that each of us can see unless you have infrared sensitive glasses or a telescope or scope or something like that. But everything is emitting black body radiation. And so that's the background. And then the story moves to Bell Labs in the 1960s. And Bell Labs was like the greatest research outfit on Earth before they broke up AT&T. And one of the things they were working on was microwave emissions and how to use microwaves for communications. This was before cell phones. And so there was going to be, they were going to try to bounce microwaves off a big balloon by sending up a signal somewhere in the United States. And then there'd have to be another antenna that could actually receive this signal. So this was an attempt at unwired communication, which would be fantastic. All right, so Penzias and Wilson were in charge of building this antenna. So they built the antenna. You can see it there in the background. And one of the things when you're building an instrument is that you always want to be able to control the noise. Signal to noise is you want to maximize your signal to noise. All of us who do experimental work are worried about that all the time. And Penzias and Wilson noticed that there was background noise to their antenna, and they wanted to get rid of it. So they checked all the electronics over and over again. They thought maybe it was pigeon droppings in the antenna. They got in and cleaned it by hand. They did everything they could to try to get rid of this noise. They couldn't get rid of it. And so Bell Labs is in New Jersey near Princeton, and they went over to Princeton and talked about this problem they were having with their antenna. And some of the physicists there said, oh, maybe that's the background radiation of the universe that would be predicted by the Big Bang. And a physicist named George Gamow had predicted that many years before, and this was exactly what he had predicted. So they went and plotted up their data and found that the noise that they were hearing on the instrument exactly fit a black body curve for 2.7 degrees Kelvin. For this, they received the Nobel Prize. George Gamow, who had predicted it, didn't receive the Nobel Prize. Other people at Princeton who'd been working on more refined predictions also didn't get it. But by this serendipitous accident of actually making the measurements that showed that the universe was a black body, they've become perpetually famous. So the way this works is that the universe is originally incredibly hot, but it's very small. And as it expands, it gets cooler and cooler. Expanding things cool down. So today, with the universe being so huge, it is cooled down to the temperature of 2.7 degrees Kelvin. And that shows that the temperature is homogeneous throughout the universe, which you wouldn't expect otherwise, which supports also that all the universe initially had the same temperature early in its history. So this result was striking confirmation of the Big Bang. And when the calculations went into trying to say what was the temperature early on and what would it be after 13.7 billion years of expansion, it would turn out that the universe would have cooled to a few degrees Kelvin, very similar to what's observed. There's more wonderful detail now as they've sent up satellites to measure the cosmic background radiation much better. So using this, they can get many more significant figures to the universe's temperature, and also they can get very slight variations in that temperature, which tell interesting details about the early history of the universe. So to sum up, all of this is driven by curiosity and serendipity. So natural curiosity leads to the measurement of distance. Step by step, the distances to ever more distant objects are able to be determined. Natural curiosity leads to the discovery of the elements in the periodic table and the discovery that elements emit light of particular wavelengths. This leads to the discovery of the red shift and that all galaxies are moving away from each other. The red shift alone is not evidence for the Big Bang. It's just evidence for an expanding universe. But the correlation between the velocity determined from the red shift and the distance of the galaxy suggests the formation of the universe at a single spot and single time. The Big Bang hypothesis then led to predictions of a cosmic microwave background, and this was discovered by accident, but turns out to be convincing proof of the hypothesis. And the gradual understanding of the laws of nucleosynthesis led to a predicted hydrogen to helium ratio that corresponds with what would have happened during the Big Bang. Therefore, there's this overwhelming evidence accumulated over thousands of years, hundreds of people working on the problem, that shows that everything in the universe, everything we can see, all the energy, all the matter, was formed in a creation event 13.7 billion years ago. The universe is a system, a single entity, the result of an event of almost inconceivable magnitude occurring in the distant past. So the key evidence for this is the Hubble diagram. And so you should be able to look at this and know what each data point represents. How is the distance measured? How is the velocity measured? How from this diagram do we get the age of the universe? And what is the ultimate fate of the universe? Is it going to expand and expand until it finally reaches a stopping point and then it contracts again, going into a big crunch? Well, the key to that is that these data points are not an exact straight line, they're slightly curved. And when astronomers recently have made very precise measurements of the most distant galaxies, they find out that it's not exactly a straight line. You have these points that are slightly off the line. So, sorry, the axes here are reversed. So here we have redshift on the vertical axis, here it's on the horizontal axis. So this slight tilt off lower here is this slight tilt upper here. And the evidence from that is that the universe is accelerating, it's speeding up. And so the universe is not going to go into the big crunch. It's going to expand forever. And as it expands, ultimately things will die. Even stars will die. Why is it accelerating? That's a puzzle. Because it's expanding like this, and there's gravitational forces pulling it back together again. So shouldn't it be slowing down? Now, the only way that the acceleration of the universe could be explained is if there was a force that was countering gravity, was stronger than gravity, and could lead to the universe speeding up. And that force is dark energy. And you can calculate what the value of dark energy must be, and therefore how much of the universe this dark energy makes up. The other mystery was that by looking at the interactions of galaxies, you could determine what the mass of the galaxy had to be. And the mass of the galaxies was far greater than the mass of the stars of which the galaxy is made up. So there's something else very massive that we can't see, and that was called dark matter. So if you look at the composition of the universe, and mass and energy are equivalent, because this by the formula E equals mc squared, you find that intergalactic gas is about 4.5%, and stars, planets, makes up about 0.5% of the universe. Dark matter about 27%, and dark energy about 68%. So more than 95% of the universe is material we do not yet understand. So there are great discoveries to come, hopefully in your lifetime.